Hey there, Mr. Sutton here with the AB Calculus 3-3 Extra Practice Number 1 solutions on differentiability part 2. On this problem, I'm trying to figure out if this function is differentiable at my border value of 1. So to do that, let's test continuity first. I need the left side limit as x approaches 1. So that's going to be 1 plugged into this first rule here. 1 squared minus 6 gives me negative 5. And then for the next one, I need the right side limit as x approaches 1. So that's going to be 1 plugged into the second rule. That's going to be essentially 7 minus 12, which is also negative 5. And then we need f of 1 to complete the picture, because continuity requires the function value to match the limit. So that happens to line up with the second rule here, because we have the equals on the 1. So f of 1 also has a value of negative 5. So we see here that the left and right side limit match up, so the limit exists at 1, and it matches the function value at 1. Therefore, our function is continuous at x equals 1. But we still need to show that the limits of the derivatives at 1 match up as well. So the left side derivative of the left side limit of the derivative of f prime, that's going to be 2x with 1 plugged into it. So that's going to be 2 times 1, which is 2. And now the right side limit of the derivative of f, that's going to be 14x minus 12 is my derivative. But now I need to actually plug 1 into all that. So that's 14 minus 12, which is 2. Since the left and right side limits of the derivative match up, we can say that our function is differentiable at x equals 1. On this problem, I'm trying to figure out if I'm differentiable at the border value of 1. So to do that, let's first test continuity. I need the left side limit as x approaches 1. So that's going to be using this first rule. So I've got 1 squared rather plus 2 times 1, which is 3. And now I need the right side limit as x approaches 1. So that's going to be using this second rule. 3 times 1 cubed is going to give me 3. And then the function value, which I also need for continuity, function value at 1 uses the first rule. So it's the same as our left side limit of 3. Next, well, first I see that I have a limit that exists, equals 3, and is equal to the function value at 1. Since my limit and function value at 1 match up, that means that we are continuous at x equals 1. And now we move on to the next task, which is figuring out if the limits of the f primes at 1 match up. So left side limit of f prime, that's going to be the left side limit of 2x plus 2 if I take that derivative. So that's going to be 2 times 1 plus 2 is 4. Now I need the right side limit at f prime. That's going to be right side limit of 9x squared. And that's going to be 9 times 1 squared, which is 9. Since the right and the left limits do not match up for f prime, that means that this function is not differentiable at x equals 1. To figure out if this function is differentiable at the border value of 1, let's first find whether or not it's continuous there. So I need the left side limit as x approaches 1. That's going to be the square root of 1 using this first rule. So that ends up being 1. And now we need the right side limit at 1. That'll use this second rule. So we're doing 2 times 1 minus 1, which is also 1. And we also need the function value at 1, which happens to use the second rule as well. So that again gives us 1. Since the limit at 1 and the function value of 1, f of 1, match up, we are continuous at 1. So we move on to figure out if the limits of f prime are going to match up at 1. Left side limit of f prime, that's just going to be, let's see, taking the derivative, we have 1/2 times x to the negative 1/2. As x approaches 1 for this function, this is just going to come out to 1/2, because you basically have, or actually, yeah, you have 1 over 2 times the square root of 1. And now let's check out the right side limit of f prime. So that's going to be, let's see, just the derivative of this, which comes out to 2 no matter what. That doesn't match up with the left side limit, though. So that means our function is not differentiable at x equals 1. To figure out if the function is differentiable at this border value for the piecewise function, with negative 1 being our border value, let's first figure out if we're continuous at negative 1. So I need the left side limit of negative 1. That's going to be negative 1 plugged into this first rule. So 3 times negative 1 plus 3, which is negative 2. And now I need the right side limit at negative 1. So we're plugging negative 1 into the second rule here. That's negative 1 squared plus 2 times negative 1, so 1 minus 2 comes out to negative 1. Since the left and right side limits do not match up, that means our limit does not exist as x approaches negative 1. So we can't be continuous, and because we're not continuous at x equals negative 1, it follows that we are also not differentiable. To see if this function's differentiable at the border value negative 1, we're going to first figure out if it's continuous there. So let me check the left side limit as x approaches negative 1. That's going to be negative 1 plugged into this first function up here. So negative 2 times negative 1 is 2, minus 1 is 1. Next, we check the right side limit at negative 1. So we'll have, using the second rule now, because that's greater than negative 1, so we're approaching from the right side using this one. That's going to be negative 1 squared, which is 1, plus 3 is 4. Since the limits don't match, that means our limit does not exist at negative 1, so we're not continuous there, and because we're not continuous, we're not differentiable. On this problem, we're trying to figure out if the function's differentiable at the border value 2 for this piecewise function. So we'll start by figuring out if it's continuous. We'll check the left side limit as x approaches 2 from the left side. That'll use this less than 2 rule, so this first rule. Negative 2 squared is going to be 4, plus 3 is negative 1. And now the right side limit at 2, that uses this second rule for greater than 2. So we have 2 minus 4, which is negative 2. Squaring that gives us 4. Subtracting 5 gives us negative 1. So the limits match up and exist. So now we check the function value there, which f of 2 just happens to use this first rule, just like the left side limit. So that's also going to have a value of negative 1. Since the limit matches f of 2, that means our function is continuous at x equals 2. So now we move on to figure out if the slope limits match up. Let me take the left side limit of f prime. So to do that, I need to take the derivative of this first rule. That's negative 2x. And then if I plug positive 2 into this, that'll be negative 4. Now for the right side limit at f prime. So that's going to be, let's see here, using this second rule. Now if I were to expand this, I would end up with x squared minus 8x plus 16 minus 5. Taking the derivative of all that, the constants would go away. I would just have x squared turning into 2x and negative 8x turning into minus 8. So 2x minus 8 is what I ultimately have to plug 2 into. So that's going to be, let's see, 4 minus 8, which gives me negative 4. Since the left and the right side limit of f prime line up, that means that our function is differentiable after all at x equals 2.